Welcome to Lecture 8 of ECE 113. In the previous lecture, you learned about filters. How do we classify them according to their response? How do we classify them according to implementation? What are its key parameters? And so on and so forth. You also learned how to implement an active biquad filter using the salient key architecture or the Thomas architecture. How do you design them? You'll see examples of that in this lecture. If you want higher order filters, you cascade a lot of active biquad filters. And you also learned about filters according to their response characteristics. Do they have ripples in the pass band? Do they have ripples in the stop band? What is their transition band slope, and so on and so forth. In this lecture, I will be talking about Butterworth and Chebyshev filters and how to design them using active biquad filters. So let's look at first how to design a Butterworth filter. The Butterworth filter is an all-pole filter. Basically, every root of your Laplace transform is a pole and has the form as you see here. So the magnitude squared of the transfer function of your nth order, so this n pertains to the order, is equal to 1 over 1 plus omega raised to 2n. Okay, where if the filter is passive at omega is 0, the filter has a response equal to 1 for any order n, and for some omega sub 0, okay, if we normalize the spectrum to omega sub 0, then if omega is 1, the response of the filter is 1 over square root of 2, or it's basically the 3 dB frequency of our Butterworth filter. If you uh, if you use a frequency greater than the cutoff frequency omega sub 0, there will be an n-pole roll-off, or your attenuation increases by 20 decibels per decade. Okay. The pole locations of your Butterworth is basically, well, if it's 1 over 1 plus omega to the 2n, if we let that be s, so s is equal to j omega, substitute s there, you get this. And with that, you have this equation for your transfer function. The roots are located if this is 0. Okay? So depending on the order of your filter, your roots will be located differently. Okay? If we expand this polynomial, let's say the order is 1, order is 2, order is 3. If we expand the expression, you get these expressions respectively. And you only extract, or you only get the stable components or the left-hand poles from this equation right here. And basically, you get these roots or the stable components of your expression rather, and you get your poles. So as mentioned in the previous lecture, the pole locations of your Butterworth filter are actually on a unit circle. Okay, for the first order, it's only right here. The poles, you have the single pole you have here. Second order, okay, here. Third order, you have this, and so on and so forth. As you can see, the poles of your Butterworth filter are equally spaced in the arc length of your unit circle. So basically, the angles between them are all equal. Okay. So ideally then, your transfer function for your Butterworth filter, this is the square of the magnitude. You take the square root of that, you get 1 over square root of 1 plus omega raised to 2n. And if omega is 1, let's say your filter is normalized to some natural frequency or cutoff frequency omega sub 0. If omega is 1, you have your cutoff. It's actually an ideal Butterworth filter. We generalize it with some epsilon. So a scaling factor of epsilon creates a small error here. Okay? Your 3 dB frequency would be somewhere here. Okay? And after that, you create an n-pole roll-off. Okay? To get the specifications of designing a Butterworth filter, you usually check first the maximum attenuation at the pass band and the minimum attenuation at the stop band. So it's usually given in dB, alpha max, again, for maximum attenuation for pass band. Alpha min is the minimum attenuation for stop band at some omega p, which is your pass band cutoff, and omega s, which is your stop band cutoff. So as a circuit designer, usually need to determine the order n of the filter. So let's derive that. Since the alphas are given in dB, let's convert our transfer function. Let's convert our transfer function with dB. Okay, so convert the transfer function to dB. That's just 10 log of your transfer function. So that's the attenuation. Okay, and negate that, you get the attenuation rather, and you'll get this expression for the attenuation alpha in dB. Okay, the maximum attenuation occurs at omega is equal to 1. So substitute that. So as you can see here from here, the pass band cutoff is at omega is equal to 1. That's what we defined earlier. So omega is equal to 1. We get this value for your alpha max, and your epsilon, which is an error factor, is equal to this equation right here. Just solving for epsilon, you get this. So the minimum attenuation is at some specified stop band frequency omega sub s. Substitute that, you get this, and you substitute the equation for epsilon that you got earlier. You can solve for the minimum attenuation, or you can solve the value for the minimum attenuation here. Okay, and then you can now get the relationship of omega s and you can get the relationship of alpha min and alpha max through this equation, the second equation. And now you can solve for the filter order n as a function of your attenuations and your specified stop band cutoff frequency. Okay, so this is just a normalized filter. You look at a normalizing, if you look at it as a unit filter, rather, this is just a normalized filter. Okay, let's backtrack. This is just a normalized filter. By defining a new normalizing frequency, we get your pass band cutoff and stop band cutoff. So let omega be equal to omega over omega p. We get some cutoff frequency omega p. And technically, it's not a Butterworth filter since you have a factor epsilon right here. Unless epsilon is equal to 1, it's not a Butterworth filter. So we can make it look like a new Butterworth filter with a new normalizing frequency. So this epsilon squared will be cancelled out. Okay, it will be cancelled out by getting a new normalizing frequency omega p. Okay, I hope I made sense with that. Okay, so basically, the purpose of defining a new cutoff frequency will actually normalize our filter and make it look like a Butterworth filter, since this error factor epsilon here is not really a Butterworth filter. So to make it more clear, let's have an example. So the example, we have a maximum attenuation at the pass band 0.5 dB, minimum attenuation at the stop band 20 dB. Your pass band cutoff is 1000 radians per second, and your stop band cutoff is 2000 radians per second. So the example is this. Get first your error factor, which is dependent on your maximum attenuation. This is your error factor. And now from here, you can get your filter order by substituting that from the equation earlier. So given alpha minimum, alpha maximum, and omega s. Omega s first, normalize it to some normalizing frequency omega p. So later we will denormalize that to some epsilon raised to negative 1 over n to convert our filter into a Butterworth filter. So the filter order is 4.83, which is rounded up to 5. If it's 4.01, you should round this up to 5 to ensure that your filter has enough roll-off to meet the specifications. So the filter order is equal to 5. Okay, so we have these statistics for the filter. That means now the next step is to get the poles. The stable components of this equation is on the unit circle. We have 5 poles on the left hand side of the unit circle, equally spaced in terms of angle, and you get your stable components of your filter right here. It follows that the transfer function of the fifth order Butterworth filter is equal to this equation based on the poles right here. So you get this equation right here. Okay. With this, you can get the quality factor of each, the Q factor of each transfer function. So let's separate that into 3. This can be implemented by an RC filter. This can be implemented by an active biquad, as with this. Okay, but first we need to make an RC filter that has a high input impedance and low output impedance so that there is no loading effect. And the better way to use that is to use an operational amplifier. So the operational amplifier right here has a transfer function. Since this is an inverting filter, you get a transfer function that looks like this. And you let these resistors be equal. So you have this equation for your transfer function, which is reminiscent of your RC filter transfer function. In this way, we just uh, made it such that the input impedance is high and the output impedance is low. Okay, so our cutoff, as I've mentioned earlier, to make this behave as a Butterworth filter, we need to define a new cutoff based on the error epsilon and the specified passband, and you get this value for your cutoff 1, 2, 3, 4. So that's equal to 1 over RC. Using these values of R and C, we can make this happen. All right. Next is to define the biquad filter of the second transfer function from here. So from the equations of your salient key, this is a salient key architecture, your cutoff is equal to 1 over RC times RC, and Q over omega naught is equal to this equation, which is defined by the gain. The gain K is from this operational amplifier right here. So let's say our capacitors and resistors are equal, then same omega naught is equal to 1 over RC. That's what we got earlier. With a cutoff of 1, 2, 3, 4, we get these values for R and C. To achieve a Q factor of 1.618, we solve for a gain K to make it possible. And with that, you can get this value for K, and you achieve a Q factor of equal to that. Okay. To achieve a gain K, this resistors must be set properly. So to get to sorry, the gain K is defined by RB and RA, but since there is some gain K greater than 1, we need to compensate for the gain using a voltage divider by connecting a resistor from here towards the ground. So let me draw that. So by connecting a resistor here towards the ground, we're actually compensating for the gain that is introduced by this operational amplifier. We want a Butterworth filter to have no gain. Okay? So that would mean if we connect a resistor here, we create a voltage divider. And this voltage divider right here must have a resistance that is equal to the resistor we need right here, so as to not mess with the behavior of your salient key architecture. So your second stage circuit will look like this. This voltage division will ensure that no gain will be introduced by the salient key, and the equivalent resistance of this is 8.1 kilo ohms, so as not to mess with the behavior of the salient key. Okay. So similarly, with the same procedure, you can get the third stage, and you connect them together, you get your desired filter. Okay, that's the end of Butterworth. Let's look at Chebyshev. Recall the transfer function of a Chebyshev type 1 filter. We have the magnitude is equal to 1 over this, and this Cn of omega is called the nth order Chebyshev polynomial, which is defined by this equation right here. So again, let's look at the attenuation response of your Chebyshev filter. So we have this, get the attenuation in dB, you have this equation, and substitute your Chebyshev polynomial, you have this equation. Again, epsilon right here pertains to the error factor. Okay. So now let's look at how to solve for the order of the filter for a given alpha maximum and alpha minimum. First, a given alpha maximum will define an epsilon. Okay, the epsilon will be defined by the alpha maximum. Your filter order n, given your stop band frequency, can now be solved. Okay, by by dividing or by substituting epsilon right here from here to here, you can now isolate your filter order n. Okay, so solving for filter order n from this equation, we have this big equation right here for filter order n. Just to compare, your Butterworth is based on logarithm, your Chebyshev is based on the inverse hyperbolic cosine function. Okay, and again, to make it behave like a Butterworth filter, we want our epsilon to be effectively equal to 1. So this will be absorbed again by a new cutoff frequency defined by this equation right here. So this value should cancel the epsilon. Okay, and we find an omega that cancels this epsilon, and make sure that to make sure that will be the new cutoff frequency. Okay, so now let's look at the pole locations of your Chebyshev filter. So recall the transfer function, which looks like this. So this actually defines a an ellipse in our complex S plane, and the roots are located on that ellipse. So you find 2n roots that are symmetric along the j omega axis, and at the left hand plane you get the roots that belong to your transfer function. So the roots of that is actually equal to this, and this is actually a an ellipse. Okay, so how does this look like an ellipse? From here you can actually solve for an equation. If sigma k and omega k represents the y and the x axis in the complex plane, we isolate them and we get this value, right? This equation rather, which defines an ellipse in our complex plane. Okay, so this circle right here represents this sigma squared plus omega squared is equal to 1. If we have a Butterworth filter, the poles of the Chebyshev filter would be located on this unit ellipse right here. Okay, so now this is the steps on how to design a filter of Chebyshev filter rather. So first, find your error factor epsilon and the degree n. We determine the parameter a, compute for the hyperbolic sine of a and hyperbolic cosine of a. You find the Chebyshev poles and you calculate the pole frequency and its Q factor. So unlike the Butterworth filter, each stage of your Chebyshev filter has a different cutoff frequency. So that's the difference between the Butterworth and the Chebyshev. The properties of the Butterworth that ensure a maximally flat response would mean that each stage of the filter must have the same cutoff frequency, but the Butterworth filter is different. So the cutoff frequency is dependent on the sigma k and omega k and its quality factor defined by this. So the quality factor can be solved by using the value of the pole. Okay, so each stage of your Chebyshev has actually a different cutoff frequency. Example. So to illustrate that, let's have again the same specifications as we used for the Butterworth earlier. But this time, let's say we have an order of 5. Okay? So maximum attenuation is 0.5 dB within a passband of maximum frequency of omega p, 1000 radians per second. The passband gain is 0 decibels. So first, calculate the error. If alpha max is 0.5, then the error can be easily calculated. You get this equation, this value right here. Solve for the parameter a, which is defined earlier. It's equal to this, and it's equal to this value. From here, you now locate the poles of your Chebyshev filter. So substitute a, and your value k here is from 0 to 4. Okay, so sorry, it's from 1 to 5 rather. Okay, so from 1 to 5 you get these 5 values for the poles, and from here you can get a transfer function for your Chebyshev filter. We can split that again into 3. So this k right here is equal to this value. We can split that into 3, as you can see here. Okay, and recall our active biquad filter. You have this value. Okay, set h is equal to 1 for unity gain. If we compare the values, if b is equal to this and c is equal to this, then q is equal to square root of this divided by this, and your k is equal to c. So your gain is actually defined by this omega naught, right? The transfer function with a 0 dB gain would be to split all these k values, and you get this, and this equation. So this transfer function ensures 0 dB gain. Okay? So first, let's look at the Q factor of each transfer function. First transfer function is just a first order filter. Its Q factor is 0.5. Second transfer function is biquad. So the Q is equal to the square root of this divided by this. It's equal to this. And finally, this has a Q factor of this. So to implement the circuit, the omega naught is equal to this, 0.36232. Okay? And with a passband frequency of 1000, omega p is 1000, you can solve for RNC. You get this circuit for your first order filter. To implement our second order active biquad filter, okay, first you get RNC. The omega p is 1000, and the cutoff of this transfer function is square root of 0.4768. So by using omega p, we can normalize that to that value, to omega p, and we get these values for the resistor and the capacitor. Okay. Next is to solve for the gain based on the Q factor. So from the Q factor, which is the square root of this divided by this, you get a gain of 2.15. So an appropriate value of that would be RB is this, RA is this. And finally, to compensate for the gain introduced by this op-amp, you use a voltage divider whose output resistance is the same as uh, this uh, resistance right here. For the third order, uh, for the third circuit rather, for your fourth and fifth poles, the circuit implementation has the same procedure as the previous one right here. So same, to normalize it to omega p, you must equate this, the square root of this, with 1 over omega p RC, solve for R and C. Solve for the gain through the Q factor, you get a gain of 2.7755. So you have uh, the appropriate resistors would be this and this. And finally, to compensate for the gain, you use a voltage divider whose output resistance is equal to this value. And the appropriate resistors for that is equal to this and this. So to compare, not to compare rather, to add things all up, this is your first order filter, this is your second order biquad, and this is your another second order biquad. This is the first circuit I've shown you, this is the second, and this is the third. And if you look at the transfer function of the total, you multiply all these, you get this response for your Chebyshev filter. You don't see the ripples since the scale of the of our y-axis is actually large. Okay? So after 1 decade, your attenuation is already negative 100 decibels. So it's that useful actually. So just after 1 decade, it's already a large attenuation. Okay? So just to compare our Butterworth and Chebyshev, the Butterworth has a maximally flat response as compared to Chebyshev, who has a ripple in the passband. It's the Butterworth is monotonical in both passband and stopband. Chebyshev is only monotonic in the stopband. It means it's just steady decreasing. So it's steadily decreasing. Here it's a steady flat in the passband and then steadily decreasing in the stopband. Okay. Your Butterworth for all orders n, your omega is equal to 0, you have a value of 1, okay, which is a low pass response. If your omega is 1, assuming we normalized it, then we have a value 1 over square root of 2 as a response for any order n. For your Chebyshev, depending on your order, the value of omega is 0 is different. Okay? And actually, your omega 3 dB changes with the value of n. Okay? For large frequency and pole roll-off, so the attenuation increases by both of them, rather, the attenuation increases by the order of your filter. In terms of equations, your Butterworth has a stop band attenuation equal to this. Your Chebyshev is only approximately equal to this value. Okay. Q factor is easily defined since all of the all of the all of the poles are on a unit circle. So the Q factor has a simple equation. Compared to your Chebyshev, well, you have this large equation right here for your Q factor, but you don't need to memorize all that. You just need to understand how to design these filters using a biquad implementations, right? So you don't need to memorize all this. It's just a summary. And that's the end of this lecture. If you have any questions, do not hesitate to leave a comment in the comment section below. Thank you for listening. I'll see you next meeting.